Okay, so you have learned all there is to know about parallel plates. Well, almost all there is to know about parallel plates. Now let's talk about a new shape, because you are probably sick of parallel plates. So in this video, we're going to be talking about the hollow conducting sphere. By the end of this video, you will be able to determine the electric potential and electric field due to a hollow conducting sphere. So let's go ahead and start by talking about what on earth a hollow conducting sphere is. So a hollow conducting sphere is going to be, so think about a basketball. Inside the basketball, we have empty space. Outside the basketball, we have empty space. And on this very thin surface here, we have charge at a constant charge density. So that is what I mean when I say hollow conducting sphere. So let's start by talking about the outside of the sphere. So that is all of this region out here. Let me go ahead and undo that because it's hard to write. So what's really cool is outside of the sphere, we actually can treat our sphere like a point charge. So what we'll do is we will actually, so what something outside of the sphere would experience is the same electric field that they would experience for a point charge that was located at the very center of the sphere. So our equations are the same as they are for a point charge. Our electric field is going to be given by kq over r squared, and our electric potential is going to be given by kq over r. So that's outside the sphere, nice, easy, and straightforward. So let's talk about inside the sphere. So what I've done is I have drawn two cones that have the same angle of separation from my point here in the sphere. And cones are super interesting, and what is particularly interesting here is that if I put a test charge at this point here, the force acting on it due to this part of my cone and the force acting on it due to this part of my cone are actually going to be equal and opposite. So it'll get pulled towards both of my cones by the same amount, and it'll actually feel a force of 0 newtons. Now, the other thing that we know is that if these two angles are equal, these two angles must also be equal. So, the force in this direction and the force in this direction are also equal and opposite. Now, if you want to know why these forces are equal and opposite, and all the ways that the geometry of our cone builds into that, I'm happy to talk to you about that. But we're not going to get into that right now. What's important to know is that our force at any point in space within our charged sphere is 0. And if our force is 0, we know that force is equal to E times Q. And so if force is 0 and Q is non-zero, we know that electric field must also be 0. So inside of my sphere, my electric field is going to be 0. So my electric field is 0, and I know that my electric field is equal to the negative of my change in voltage divided by my change in distance. And so if my electric field is 0, that means that delta V equals 0. So my voltage, my electric potential, must be constant within my charged conducting sphere. So if I depict my electric field versus my charge graphically, what I'll get is I will get an electric field that gets asymptotically high. So it's going to get very, very high the closer I get to my hollow sphere. And you'll also notice here that my electric field is going to be dependent on 1 over my distance squared. And that, again, is the same as my electric field for a point charge. But then as soon as I get inside my sphere, as soon as I hit the radius of my sphere, which as you can see here is 0.5 meters, my electric field will immediately drop to 0. So that is going to be how I figure out A, the radius of my sphere, and then B, I can also use this to figure out that this is an electric field versus distance graph. I could do the same for my voltage. So again here, I have that characteristic 1 over r. V is dependent on 1 over r curve once I leave the radius of the sphere. And I have a flat line here. And so here I can see that this sphere has a radius of 1 meter. And I can see that here from the plate by looking at the point where my graph becomes a straight line. Because it's only after I get into the sphere that my voltage becomes constant. So takeaways. Outside of a conducting sphere, like that of a point charge, and inside of a conducting sphere, the electric field is 0 and the voltage is constant.